In this video, we learn about differentiation from first principles, and in particular, we're going to see how to derive the formula that allows us to find the derivative f dash of x. Now, given a function with a curve y equals to f of x, the gradient at any point along its curve's length is given by the derivative function f dash of x. And the formula that we're going to be deriving in this tutorial is the following. F dash of x equals to the limit as h tends towards 0 of f of x plus h minus f of x over h. If this doesn't make any sense to you right now, do not worry. This is exactly what we're going to be explaining in this tutorial. When we differentiate with this formula, it is known as differentiating from first principles. Now let's go ahead and see how this formula is derived and what it actually means. Okay, let's say we're given a curve like the one shown here, with an equation y equals to f of x. That's some function of x. And now we can see here that we have a point P along the length of this curve, and P has coordinates, completely generic coordinates, x, and its vertical coordinate will be, of course, the height of the curve, f of x. Now, the question we want to answer is, what's the gradient of the curve at that point P? And the way we'll answer this is by finding the gradient of the tangent to the curve at point P. Now, the tangent to the curve at point P is the line which passes through point P and has the same gradient as the curve at that point. But now, unfortunately for us, we can't simply calculate the gradient of this line. To find the gradient, we need 2 points through which the line passes, so we can use our well-known formula for the gradient of a line. But because we only have 1 point, we're going to come up with an approximation. And the idea behind this approximation is to use another point along this curve, which we'll call, say, Q. And we're going to use that point to calculate the gradient of the line passing through the 2 points P and Q as an approximation to the tangent to the curve at P. Now, Q has coordinates, we'll say x plus h, where h is the horizontal distance between points P and Q. The vertical coordinate of point Q will therefore be f of x plus h. Done. So the gradient, therefore, if we write it here, gradient will equal to, well, it's the well-known formula, y2 minus y1 over x2 minus x1. Or in this case, given we're dealing with P and Q, we can write this as yq minus yp over xq minus xp. And as we've just seen, those points have coordinates x f of x and x plus h f of x plus h. So that would be f of x plus h minus f of x over x plus h minus x. And that leads us to f of x plus h minus f of x over h. That's the gradient of that line. Done. Now, as a first approximation, this blue line doesn't look too bad. We can see it's relatively close to the tangent to the curve at point P, but we can make this better. And indeed, we can make this better by making this distance h smaller. By making the horizontal distance between these 2 points smaller, Q will move along down the curve closer to P. And the closer Q will be to P, the better the approximation to the tangent to the curve will become. So let's go ahead and do this. We'll just erase all of this. Okay, so as a second approximation, let's take point Q here. So that's our new point Q, and therefore its horizontal coordinate will be x plus h. Remember, h is the horizontal distance between the 2 points, that's h, and its vertical coordinate will be f of x plus h. Now, if we draw the line passing through the points P and Q, we can see that we're definitely getting closer and closer to the tangent to the curve. This is a good approximation. And again, its gradient would still be given by this formula, f of x plus h minus f of x over h. The only difference here, with what we had before, is that we've made this horizontal distance, h, smaller. And that's going to be the idea here. We can go even further than this and make our approximation much, much, much better. Because there's no limit to how small we can make h. If we wanted to make h equal to 0.000000001, we could, and this formula would still work. And here comes the calculus. We're going to take the limit as h tends towards 0. What that means is that we're going to look at this gradient formula in the limit as h tends towards 0. That means we're going to consider this by letting h become infinitely close to 0. Careful, not equal to 0, but infinitely close to it. Now, the way we write that is as follows. We write the limit as h tends towards 0 of this formula, f of x plus h minus f of x over h. And this is the definition of the derivative function. That's f dash of x equals to this limit as h tends towards 0 of f of x plus h minus f of x over h. And so that's the idea here. We can see here that all that f dash of x is, it's the gradient of the line passing through 2 points P and Q. The only distinction that should be made between this definition and this formula for the gradient is the fact that we're letting h become infinitely close to 0, which leads to these 2 points being indistinguishable. Now, if we erase this very quickly, the scenario that we end up with here is the following. P and Q are so close that we cannot distinguish one from another. The line passing through points P and Q, therefore, becomes indistinguishable from the tangent to the curve at point P. This formula, therefore, leads to the gradient of the curve. And that's the derivative function. In summary, given a function f of x, its derivative function f dash of x can be found using the formula f dash of x equals to the limit as h tends towards 0 of f of x plus h minus f of x over h. When we differentiate a function using this formula, it is known as differentiation from first principles. Now that we've seen how this formula is derived, we're going to move on and actually work through some handwritten examples to see how to use this formula to find the derivative of a function. I hope that helps.